Oops. Okay. No audio. Stay co-host. Oops. Okay. Okay. My apologies. I left the meeting, so now I'm back. So good afternoon, everyone. Welcome to the second lecture of mathematical methods for physicists. And thank you for being with us yesterday and also today. Soon the homework will be distributed. And yesterday we had on Zoom, we had 220 people, and on YouTube channel, we had 140 people attending the course. So this is just a statistic providing you. Today, we have 100 people, 101. So I think slowly but surely people are showing up on the Zoom platform. So I don't know if whether you had any questions. If there is any question, Dr. Riyad, Jamil, or other colleagues here, they can bring it to my attention. If there is no question, we can start the rest of the course. Okay. So I
so far,
yeah.
Sorry, Doctor. So far, there is no question. You can start the lecture.
Okay. Beautiful. So if you have any question, you can type it in Q&A, and the moderators that they are here kindly, they can bring it to my attention, or they can answer them in real time. Okay, thank you very much. So let's start with the course, and let me share the screen. It takes a while. Okay. You should see the screen, right? So yesterday we introduced vector space, and mainly we use the three-dimensional formalism. And when we define the vector in A, and let's say vector in B, and then we say how to sum them up. And also, if you have a scalar quantity, how essentially we are dealing with A times the vector A. Okay. And from these, we got some properties, which I don't want to repeat them, but we got them to be commutative. For example, A plus B is equal to B plus A. And we define a negative of a vector. We define a zero vector. And also we looked into some other properties like associativity of plus product. Plus sign, and etc. And then we say, well, okay, let us define. You have two vectors, and let's define from these two vectors a scalar quantity, and we define the dot product, which essentially was given by A multiplied by B, and the cosine of angle between A and B. And indeed, that was all geometrical approach. And on the other side, also, we say that if you look at the algebraic approach for example, in the three-dimensional space, that vector can be determined with three components. And we say that there is a huge difference between a scalar quantity of A and a vector of A. So a scalar quantity under a rotation, of coordinate, remains the same. So if you do a rotation from the coordinate of black, which is X and Y, to new coordinate of x prime, which is the blue one, and y prime, you do a rotation of angle of phi. And then what you will see that in here, a is equal to a prime. So if you do the rotation, while for the vector of a prime, then each of the component, they will be linked to the component of the non-rotated coordinate with a certain relation. And this relation was that a prime I is equal to summation of aij, a of j, and j is the index that repeated index, which is going from 1 to, let's say, 2 or 3 or n for n-dimensional space. So that was the definition also that we had it for the vector, and I say that be careful with this definition because we will be using it to define also the tensor, and that's extremely important. So when it comes to the A dot B, well, we say that, well, that was a geometrical approach to determine the value, but also we looked into the algebraic approach, and the algebraic approach was that is given by AI, BI, which is I summing from 1 to 3. And indeed, we showed that this is a scalar quantity. This is a scalar quantity. And how did we show that? We showed that this is equal to summation of A prime I, B prime I, which is I from 1 to 3, which is indeed is equal to A prime dot B prime. So that was one kind of product of the two vectors. And the concept was the projection. So indeed, A dot B is essentially projecting A onto B or vice versa, because that's a commutative operator, or essentially the product, which is equal to B dot A. Okay, lovely. So so far we were good, and now I'm introducing a new kind of product, and this product is again determined between two vectors. But the difference with a dot product is that this brings you to a vector space. So, well, is a specific vector, which it's very, very useful. How do we define this? Indeed, it is given by a cross sign. So you have two vectors of A and B, and then what you will do a cross product between the two, and this we call it cross. Okay, or in LaTeX, we write it as a times. Okay, and the result is a vector. Well, I have to be a little bit careful. Later on, you will see that is a pseudo vector, has some strange properties. So, well, for the time being, let's call it a vector. Well, when we talk about a vector, geometrically speaking, we have to speak about a magnitude and also a direction. This is the geometrical way which we define the vector. Okay. So A cross B, if we call it a new vector C, then the magnitude of vector C is given by A, B, not the cosine, but here is a sine of A and B. Okay. And what about the direction? So this is the magnitude. And the direction indeed is that A, B, and C, they form a right angle. So let me tell you what does it mean. For example, assuming that's a geometrical approach, and this is the vector of A, this is the vector B, then definitely vector C is orthogonal to the plane that A and B they are creating. And the way that is a right angle, they form a right-handed handedness, is that if you move from A to B, then the direction of your right hand, or the thumbs, will indicate the direction of C. So A, B, and C, they form in this way. Not necessary that A and B, they are orthogonal to each other, is not needed. But what is needed is that C definitely is orthogonal to A, and C also is orthogonal to B. Okay, that's a very, very important property that you do have. And look at the magnitude. Look at the magnitude of C. So the magnitude is A, B, sine of A and B. Well, assuming that you have the vector of A, and that's a vector of B. So if you make an orthogonal line to the vector of A, which is that orthogonal line, so and that angle is essentially the angle between A and B. So you can call it either theta, or you can call it phi, or whatever you want to call, or alpha. And indeed, the orthogonal length here essentially is B multiplied by sine of alpha. So, and indeed, if you want to calculate what is going on with area that is created by the two vectors of A and B with a parallelogram that you have it here, indeed, the surface that is created here is A, the magnitude of A multiplied by the orthogonal length that you have it here. So it will be A, B sine of alpha. So indeed, this value will give you the surface. Oh, let's be careful. Let's call it area created by the two vectors of A and B. Okay. So, well, the dot product will provide you the projection, while the cross product, what it does, that is true that is a vector orthogonal to an A and B, but also on the other side, it provides you the surface created by the two vectors. So if vector of A is parallel to vector of B, so means that A is, for example, like this, and B also is parallel to that one with any magnitude or opposite direction, then the A cross B, which is the surface created by these two, is equal to 0. Okay? So whenever you want to check if two vectors are parallel to each other, what you have to do the cross product. So this, what I describe here, is fully the geometrical picture. And now slowly we have to go and also determine the algebraic representation. So assuming, well, before going with this, let's consider that the three-dimensional Euclidean space that we do have. So we have X, Y, and Z. This is what we define. And then we have three vectors of X hat. We have Y hat. And also we have Z hat in this direction, which all these three vectors, they are unit vectors. And then let's choose what is going on with X cross product of Y hat, X cross product of X hat, X cross product of Z hat. So X cross product of X hat is 0, as we described, because the two are parallel to each other. X cross product of Y hat will be the magnitude will be the magnitude of X hat, which is 1, magnitude of Y hat, which is 1, and then the sine of vector of sine of the angle between X and Y, which is 90 degrees, that will be again 1. So, and the direction will be given from you move from your hand, you take your right hand and you move your index finger and the rest towards from X direction to Y direction, and the thumb will indicate the direction of the new vector. So if you go from X to Y, then you have the Z. So indeed, that will be the unit vector in that direction. While if you go with X multiplied by Y, you will see that that will be equal to minus Y hat. Okay, so indeed, I can tell you a simple relationship. You can go with the permutation that you have. So whenever you want to calculate the X, the cross product, so what you do, you multiply X by Y, you will get Z. So you go right, whenever you go clockwise, you will get a positive sign. Whenever you go counterclockwise, you will get a negative sign. So for example, the product of X by Y, you go clockwise, then you will go with a positive sign. X multiplied by Y will be positive sign of Z. And assuming now I will go with a different, so assuming that Z multiplied by Y, then Z hat multiplied by Y hat, you go counterclockwise, it will be negative sign, and the result will be X hat. Okay, so these are the relationship. And now let's use this relationship and doing the algebraic approach. So you have A cross B, so which A is given by AX X hat plus AY Y hat plus AZ Z hat. And now you do the cross product of BX X hat plus BY Y hat plus BZ. Plus BZ Z hat. So the result will be AX X hat cross product of, let's write it with a different color just to distinguish. So cross product of BX X hat and the rest, which I will not discuss that for the time being. So that will be AX BX, but then I have X hat cross product of X hat that will be equal to 0. While the second term indeed will be equal to AX X hat plus, cross BY Y hat plus AX X hat cross BZ Z hat. So the result of these will be AX BY X hat cross of Y hat. That we just look at the right angle that we described. So X hat multiplied by Y hat. I'm going clockwise. Then the result will be Z hat with a positive sign. And then for the other one will be AX BZ. Then you have X hat cross Z hat. So X hat cross Z hat, that will be negative sign of Y hat. So, and then I have another 6 terms, which 2 of them, again, for Y cross Y hat will be 0. Z cross Z hat will be equal to 0. And then the result, if I want to write it down, simply will be AX BY minus AY BX Z hat, then plus AZ BX minus AX BZ Y hat, and the last term will be AY BZ minus AZ BY X hat. Okay, so that will be the result that you will get for the cross product of A and B in terms of algebraic approach. So if you can expand these in terms of determinant, essentially, simply that can be given by x hat, y hat, and z hat if you write it down, because you will see that those terms, they showed up in as a vector. So the result again will be a vector. But what is going on with the second row, that second row will be the first vector. You will have ax, ay, and az. And the last row will be bx, by, and bz. So, and that's a way that we have the result of the vector that we are expecting. So that determinant, how do you calculate the determinant? Indeed, for those people that you may not know, first term that you have it will be x hat, and then you have the determinant of ay, az, by, and bz. So essentially that determinant is ay, bz minus az, by. And then you have the second term, which is this one. So since the position is 1, 2, then it will show up with a minus sign, 1. And then you have the determinant of ax, az, bx, bz. And finally, which that is ax, bz minus bx, az. And finally, the last term, which will be this. So since the position is 1, 3, that shows up with a plus sign. So it will be 1 plus z hat, and the determinant of ax, ay, bx, by. So if you do the calculation for the determinant, will be ax, by minus ay, bx. Good. So that's the way that someone can do the calculation and find out what's going on with a cross product of two vectors in algebraic approach. Well, so far so good. So I have no problem. Some people, they may have interest to not write it, the vector of A, to not write it in terms of x hat, y hat, and z hat, the way that I told you in the last time. So maybe you can write it as, but still in the three-dimensional way, A1, E1, A2, E2, A3, E3. But I remember that E1, E2, and E3, they are orthonormal, so they are orthogonal to each other and normalized to 1. And again, for B, I can define that is B1, E1, plus B2, E2, plus B3, E3. And then when you do A cross B, then indeed, this A cross B, which is equal to C, this C also has C1. I'm sorry, I have a phone call just replying to this. My apologies. So this vector of C also has C1, E1, C2, E2, and C3, E3. So it has 3 components as well. But what is happening with the component of C1, C2, and C3 to determine them, indeed, or express them in terms of the A1, A2, A3, B1, B2, B3. So indeed, C1 essentially is given by the description that I say. It will be A2, B3 minus A3, B2, and C2 will be given by A3, B1 minus A1, B3, and C3 will be given by A1, B2 minus A2, B1. So if you look at the sequence, what you will see that whenever one happens, then you have 2, 3 for A and B. So what is happening that C, A, and B, they form a right angle. So as a consequence, what is happening with the index of I that you are looking for as a result, that will be given by A, J, B, K minus A, K, B, J. Okay, so that is now you have to substitute it with I equal to 1, and then J is equal to 2, and K is equal to 3. Or if you look for I equal to 2, then J is equal to 3, and K is equal to 1. And when you look for I equal to 3, then J is equal to 1, and K is equal to 2. So they should form a right angle. So a mathematician, Italian mathematician, introduced a notation which is extremely compact and helping us to express these calculations in an easy way. And of course, it's named after him, is Levi-Civita notation. So Levi-Civita notation. Let's write it in this way. And this is, they call it also epsilon of Levi-Civita, or Levi-Civita symbol, which is epsilon, and they show it with this way, and has 3 indices, so I, J, and K. This can be defined in 2-dimensional way, it can define in 3-dimensional way, it can define in n-dimensional way, and is, by the way, is a tensor, is not a vector. Later on, we will discuss about the tensor quantity. But what is happening whenever I, J, and K, they form even permutation. What I mean by even permutations, so it means that if you have 1, 2, 3, and it goes clockwise, like this way, then the result is +1. When I, J, and K, they go odd permutation. What does it mean? That if you have 1, 2, and 3, but it doesn't go clockwise, but it goes counterclockwise, like this way, then is a negative sign. And when it's repeated, the indices are repeated, I, J, and K, they are repeated, then is a result is equal to 0. For example, epsilon 1, 1, 2 is equal to 0, because 2 indices, they are repeated. Epsilon 1, 2, 2, again, that is equal to 0, because 2 indices are repeated. Epsilon 3, 1, 3 also is 0. Epsilon 1, 3, 3 also is 0. Whenever the indices are repeated, then is equal to 0. While if we look at the epsilon 1, 2, 3, so if you look at the formation of 1, 2, and 3, the sequence of them, they go clockwise in this way. So the result is equal to 1. Epsilon 3, 1, 2, again, it goes 3, 1, and 2, then is equal to +1. Epsilon 2, 3, 1, also that is equal to +1. Okay, so that's a new function that I'm defining for you in the discrete basis. And but if you look at the epsilon 1, 3, 2, if you look at that the value of this function, so it goes 1, 3, and 2, is go counterclockwise, is -1. Epsilon 2, 1, 3, that also is equal to -1. Okay, epsilon 3, 2, 1, also that is equal to -1. So whenever you go with odd permutation, the result is -1. When you go with even permutation, the result is +1. So if you use the epsilon ijk notation, then A cross B, which is a new vector, as I say, is a vector of C. Then if you look at the I component of the vector C, which is means that I'm looking for A cross B, the IS component, then is simply given in terms of epsilon I j k, A j b k. So I'm looking for the I component. So the first index is I component. Then the second index j, indicating the first vector that I have it in the calculation. And the third index determine the bk, which is choosing the second vector. And indeed, you have to sum over all possibility of I and k. So you are looking for the I component, you have to sum over j and k. Let me look at the results. So I'm looking for A cross B. Why I'm spending too much time on this? Because epsilon ijk is extremely useful. It can simplify our life in an amazing way. So look for A cross B, the first component. So what I will do, simply that is given by summation on j and k, epsilon 1, because that's I, and then summing over j and k, that will be A, j, b, k. But now j and k, they are changing from 1 to 3. So let's expand it. So you have epsilon 1, j can be 1, k can be 1. So if you have A1, B1, epsilon 1, j can be 1, k can be 2, so it will be A1, B2, epsilon 1, 1, 3, A1, B3. And now I'm going with other epsilon 1. Now the index can be 2. The other one can be 1. So A2, B1 plus epsilon 1, 2, 2, A2, B2 plus epsilon 1, 2, 3, A2, B3. So, and etc. So, but when you look at the definition of epsilon ijk, you will see that here the index is repeated. So definitely that is equal to 0. The index is repeated is equal to 0. The index is repeated is equal to 0. Here also the index is repeated is equal to 0. Here also is 0. That's the only term that is not equal to 0. Epsilon 1, 2, 3. And if you look at the 1, 2, 3, you will see that it goes clockwise. So the result of these will be positive 1. Okay?
Yeah, doctor, sorry for interrupting. We have a couple of questions. The first question says, can C sub I be written for n-dimensional vector space in the form you just mentioned?
Can CI be written for n-dimensional vector space? I assume Subra Mondal is asking this question. I assume
Yes.
that the question is related to the cross products, right? No. Okay. The result, the simple answer is no. You will see it when you go to, you will go to determine the cross product, then you have to define it in the 3-dimensional space. And if I'm not mistaken, also can be defined also in the 7-dimension, not more than that. In order to determine similar to what I described here, you have to go with the wedge product, which it will be the subject of the exterior product in the tensor and manifold calculation that we will be discussing at the end of chapter 2.
Great. We have a second question from Mr. Serwer. He says, x hat cross product x hat equals 0 means cosine theta should be 0, means that theta is 90, so they both perpendicular.
No. Okay. Don't get confused. So we have x hat. Here we are talking not about dot. We are talking about cross x hat. Okay. x hat cross x hat is equal to 0, because we say that these two, they are parallel to each other. So it means that the result is 1 multiplied by 1, and we are talking about the magnitude, by the way. Let's write it, the magnitude. So it is 1 multiplied by 1, which is the value of x hat, a value of x hat. And then you have the sign of x hat and x hat. The sign of x hat and x hat, what is the angle between x hat and x hat is 0. So the sign of 0 is equal to 0. So that the entire of this is equal to 0. Okay.
Another question we have, he say, it's an anonymous attendant, how to build epsilon ijk LC symbol for n dimensions, just extension to epsilon ijkl, etc.
Yeah, indeed. You can define epsilon ijkl whatever, and for n dimension, as soon as I, j, k, l, m, etc., they will form a right form the right permutation, which is even permutation. Okay, that the result will be +1. If it's odd, that will be -1. Okay.
The last question from Mr. Amir Hussein. He says epsilon 132 A3 B2 is missing.
Yeah, I have not finished that. I have not finished this. So this is what I say, that you have the dots, but I was interrupted by the questions. I mean, what you say. Okay.
Okay, that's it.
No,
That's
no
it. You
worries.
can continue.
Yeah. So, and then if you do the rest of the calculation, you will have epsilon, for example, 2 to 2, which is A2, B2, epsilon 2 to 1, which is A2, B1, and etc. And as Amir Hussein says, that we have epsilon 1, 3, 2, A3, B2. That's the only other one which is not vanishing. So indeed, that is equal to -1. Because if you look at the permutation of these, it goes 1 and then 3, and then you have 2. So if you look at the orientation of that, then indeed you will see that it goes counterclockwise. That's the reason that you have -1. So indeed, the result of A cross B, the first component will be A2 B3 minus A3 B2, which is lovely, which is exactly what we had it in the previous terms. This is the result that we had, right? Oh, yeah. So epsilon ijk, as I say, is wonderful because it allows us to compact our calculation. Do you remember that we had the cosine components, Aij? Do you remember that? And I say that Aij, A, Kj, the summation on J, that will be equal to delta of Ik. That was the orthogonality relationship which we had in the previous lecture. Here, epsilon ijk, epsilon Lm, oh, let's go with something else. M and N, K, if you sum over K, also has a very interesting property. So you can take two epsilons. What you do, you keep the last index repeated. So indeed, what you do, you sum over, let's say 1, 2, 3 for these, and the result is very interesting. The result, it will be delta Kronecker of Im, delta Kronecker of Jn, minus delta Kronecker of In, delta Kronecker of J and M. Try to prove this. what you need to do is just substituting them together. These are very, very important property, which we will be using them when we go with two cross products. And when you go with two cross products, you will get amazing. You can simplify things with this approach. Okay. Lovely. I don't believe that there is any question further. So cross product appears in physics in many different parts. So, for example, in the classical mechanics, angular momentum is given by R cross P. Okay, which P is a linear momentum. R is the position that you have. Okay, and that is, of course, angular momentum. Well, that is the classical version. The quantum version is that the operator of angular momentum is given by R cross P. Okay, and remember here, R and P are respectively position and momentum operators. Okay, it's for the people that you have not taken the course of quantum mechanics, just don't get scared. I mean, I just want to tell you that in the quantum mechanical language, L, which is defined in the way that I have written above, is an operator. So, and strangely, L cross L is not zero. Okay, so you have to know what you are going to do. So previously I said to you that any vector cross product of itself is equal to zero because the angle of the two is equal to zero. So however, I'm warning you that is not true when it comes to the quantum mechanics language. When it comes to quantum mechanics, you have to be treating L as an operator. So that will be R cross P cross R cross P operator. So which is acting on a function, and you will see that it has certain value, which is again given in terms of L operator. Okay. And also that again, the cross product appears in for example, angular velocity. It appears in the magnetic force. So if you have a particle which is moving with a velocity of v, and then it sees a magnetic field, then the force that these particles see will be equal to v cross p. Of course, the charge of particle exists there as well. So remember, that's a very, very important property that you do have it for the cross product. So let me see. So far, we are now okay to know two kind of dots, which is A dot B and also A cross B. So this is a scalar quantity, and that's for the time being a vector quantity. Okay. So we have the plus, we have the scalar product as well, and here we have also two kind of products, which is the dot product and the cross product. Now let's work with three vectors, A, B, and C. What we can do with the dot, I mean, just placing the dot and cross. So the first thing that we can say, well, we can say that this cross all of them together. What is the result? You can write it in Q&A. A cross B cross C.
There's two questions. One of them.
Okay, let's stop here and reply to the questions.
Okay, the first question from Mr. Nechirwan. He says L cross L is not equal to zero because of they are in Hilbert space, or what?
Because it's an operator, okay? Because it should act on a function. Okay, when you do the calculation, you will see that the operators, they will not commute with each other. Then that's a result. We will see that later on.
Okay, the second question says, how can cross product be dealt between three vectors? I mean, just like A cross B cross C, can you just give a little explanation about it quickly?
Absolutely, I will do that. So let's read the rest, what they say.
Next question from Mr. Amir Hussein.
Oh, no, they're answering to my question. So I asked it, what is going on with A cross B cross C? And the people, they say that is written with B, A dot C minus C, A dot B, and A cross B cross C. This is what people, they say answer is A cross B cross C must be equal to 0. So, and they say that it should be equal to 0. And some other people, they explain it in a different way. Wonderful. Okay. So let me tell you, well, this result is a vector. Okay. Because A cross B is a vector, cross C also will be a vector cross another vector, which is a vector. Now I have to tell you where is the location of the cross. So I will go with that. Okay, we will do the calculation for this in a few minutes. What about A, B, and C? Can I do dot here, guys? I want to see the Q&A. Can I write this? No, no. Okay. So I see people, they saying yes and no, and it's going completely with a random way. So no, I cannot write this. Why? Because B dot C is a scalar. Okay. And dot is defined only between vectors. So you cannot have a vector dot product of a scalar quantity. So this doesn't exist. Okay. So let's write in a different way. A now cross B dot C. What is the result of this? What is the result? Is a vector or is a scalar? Scalar, scalar. Oh, yeah. All people, they reply properly. So indeed, the result of this is a scalar. So what we have to do, indeed, A cross B is a vector. Dot product with a vector is a scalar. So essentially, I'm not going with placing where is the cross and where is the dot. But remember, when I write it in this way, I allow you to respect the rules. So if I write A cross B dot C, means that I don't expect you to have the parentheses here, because B dot C will be a scalar. Okay. And the scalar will not be a cross product with a vector. So this is what I'm telling you. Indeed, you have to be very careful when I write it in this formalism. Indeed, the position of the parenthesis is you should assume it that it's given in a proper way. So you cannot put the parentheses in this way. So indeed, the only way that the parenthesis is allowed is the following one. Okay. So let's do the calculation. That's the first case that we have to do. Do we have other things? I have A, B, and C. Do I have other options to place dot and cross? So I have two places. What I can do, I can place the cross there. Okay. I can place the dots, which is it's not permitted. I can place cross and dot, or I can place dot and cross, which is later on I will show to you that is identical. Okay. So now let's do the calculation for either A cross B dot C or A dot B cross C. Okay. This is what I have. Well, we call these the triple dots or the triple products. Okay, let's do the calculation here. I will go with the first one. What is going on with A cross B dot C? So first, I have to do the calculation of A cross B. So A cross B is indeed, we have done the calculation. I want to expand it in a proper way. It will be X hat A2 B3 minus, minus A3 B2 plus Y hat A3 B1 minus A1 B3 plus Z hat, which is equal to A1 B2 minus B2, A2 B3. Okay, good. So far, so good, right? So, and now this is A cross B. I will do a dot product with C. What is the vector of C? Is C1 X hat. You can write X hat at the front or at the end. It doesn't matter really. The second term is Y hat C2, Z hat C3. And now I do the dot product between this vector and this vector. So, and can you tell me A cross B dot product with C, which will be the first component of this multiplied by the first component of that, which will be A2 B3 minus A3 B2 C1. And then plus, remember the result is a scalar, so it should go with a plus. Then it will be the second term, which is this one multiplied by C2. So the result will be equal to A3 B1 minus A1 B3 multiplied by C2. And then the last term, which is this multiplied by that. So that will be A1 B2 minus A2 B3 C3. Okay. So that's the result that I have.
Doctor, we got
Yes.
two questions, if it's okay.
Yes.
The first question from Miss Khansa. She says, L hat, I believe is cross, L hat is not 0. Why? Kindly explain. I joined late.
Yes, but this is what we described that. I mean, you can look at the video later on, but simply because L is an operator in the quantum mechanical language. In the quantum mechanical language, we say that we have to be careful. Second term, it should be A1 B3. Second term. No, it should be A3 B1.
I think they're pointing at the last term. I think it should be A2B1 instead of B3.
The second term, you mean that?
No,
one?
no, the last term. The last term, like the
Oh,
Z
this
hat
one?
term.
Oh, yes, yeah. Okay,
Perfect.
okay. A2 B2. Sorry, B1. Yes, thank you. Thank you very much. What else? Shouldn't the second term of A cross B be negative? No. I already, I already plus the negative sign and I did the calculation. So look at the, if you look at the expansions that we had it here. So that was, if you write it down, that was A1 B3 minus B3 B1 A3. So if you have these with the negative sign, then it will be y hat A3 B1 minus A1 B3. So now let's go down. Okay, remember A3 B1 with a positive sign minus A1 B3. A3 B1 minus A1 B3. No, is correct. Okay. Okay. No questions? Okay. So you can try to simplify this, but indeed that is nothing more than writing a determinant of a 3x3 matrix, which is A1, A2, A3, as you guess, of course, B1, B2, B3, and that is C1, C2, and C3. And if you expand the determinant, this is what you will get. Okay, so I can expand it further, so that will be A2, B3, C1 minus A3, B2, C1 plus A3, B1, C2 minus A1, B3, C2 minus A1, B2, C3 with a positive minus A2, B1, C3. Okay. Okay. Lovely. And what is that? The result, as one of attendees they mentioned. So if you assume that the two vectors of A and B, they lay in a surface, so let's say in a plane, assuming that the two vectors are arbitrary in the space, so I will assume at the plane which is passing through. So, and then A cross B will give me the surface of the parallelogram, which is essentially is this vector, which is A cross B. So that is the vector that I have, and the magnitude of that is equal to the surface that I have it here. Now, assuming that the vector C is not in that plane, okay, or is given here, like this way, okay. Then what happens essentially, I can look at the I have to look at the calculation of A cross B dot product with C. So essentially what I will do, I will project these, which the angle is let's say alpha. So indeed I will have A cross B, the magnitude, times C sine of theta, or sine of alpha, which is essentially is giving this orthogonal length, and then this A cross B, which is what's the surface. So is surface multiplied by H, which is the height of these this volume. And essentially the entire of this result will be the volume that is created by the three vectors, which in this case is vector A, B, and C. Okay. And indeed, if that is true, that definitely A cross B dot C is also equal to A dot B cross C. That can be seen also from the determinant. If you look at the determinant of this, essentially that is equal to A1, A2, A3, B1, B2, B3, which is, and that one is C1, C2, and C3. Okay, which is identical to what we found it here as well. So when you have the cross and dot product, without being worried, you can switch them together and still the result will be the same, but you are not allowed to change the sequences. Okay. For example, A cross B dot C, that is equal to minus B cross A, because if you, we discussed that A cross B is not commutative, is essentially equal to minus B cross A. And then that is a dot product with C. So if you look at this, the result is minus B cross A dot C. So you are not allowed easily to switch them together. So the sequence should be the same, A, B, C, and then you can swap the dot and cross product without having any problems. So do we have any questions, or we are okay? We are okay? Okay. So let's go with the second form of triple product. So the second form was A cross B cross C. And here it is important to know where is the location of parentheses. So do I mean A cross B cross C, or do I mean A cross B cross C? That is important. Okay, let's see if what it will be the result of the two. Okay, so I can do the calculation in the way that we discuss in the algebraic approach, but let's go in geometrical approach, because geometrical approach is very interesting. So assuming that I have the vector B, the vector C. So what is going on with the vector B cross C? So B cross C, that will be the vector which is orthogonal to the two of them. So B cross C. Okay. By the way, I changed the geometry. Okay. I changed the geometry. And now this is the vector A, which is an arbitrary vector in space. Remember, vector A cannot be, or let's write it in a different way. What is happening if vector A is in plane of B and C? Okay. That is one question that I have for you. What is happening? The second thing is that, well, I assume that vector B and vector C, they are in a plane. This is the plane that I have for them. And vector B cross C is orthogonal to this plane. That is B cross C. And the orientation is, as I say, is upward, okay? So assuming that you have another vector, any vectors that you do have, assuming that you have a vector like this, okay? That's a vector of A. What is happening with A cross BC? So essentially, also I can assume that there is a plane here, which vector of A and B cross C, they will be included there. So A cross B cross C will be a vector which is orthogonal to B cross C and A at the same time. Do you get that? So A cross B cross C is a vector which is orthogonal to A and orthogonal to B cross C. What is this vector that is orthogonal to A and orthogonal to B cross C? Where it should be located? Any thoughts? You can write it in Q&A. BC plane, exactly. So the result, as you said correctly, since B cross C is orthogonal to the B and C, then the only way that you have A cross B cross C, which is orthogonal to the two, means that the new vector that you have is in that plane. I don't say any directions because the direction of this should be given in a right-handed way. So for example, for this specific case, that should be in this way, okay? That is the result of A cross B cross C. So means that A cross B cross C is in the plane of A and B. Sorry. B and C, which means that this can be expanded in terms of the vector of B and vector of C. Okay? And of course, this is a linear function and etc. So someone can do a little bit of mathematics, and what they will get, as you explained in the chat room, that will be given by B. And what is this coefficient? Is a scalar quantity. What is this scalar quantity? A dot C. And then plus C. What is this scalar quantity? Minus A dot B. Okay? So indeed, that is given by B, A dot C, minus C, A dot B. Essentially, they call these A cross B cross C, they call it back cap rule. Okay? First, you have to write B, and then A dot C, then you have to write C, A dot B. Okay? The result, remember, what is the result? Is a vector. Okay? And the coefficient of those, let's say, vectors will be given in terms of A dot C and A dot B. So if A, B, and C, they are in the same plane, what is happening, guys? A, B, and C, they are in the same plane. I am looking at the chat room. Let's see the result. Exactly.
They're saying the answer is 0.
The answer is 0 because if these two, they are in the same plane, indeed means that A is in the plane of B and C, then B cross C dot A, or A cross B C, that will be equal to 0. Lovely, fantastic. Okay, good. Let's drive this from algebraic approach. Do you remember what was A cross B cross C? Can I call this a new vector of D? Do you agree with me? Okay. So this is essentially A cross D. But remember that D is B cross C. Lovely. So I have A cross D, and I'm looking for the I component of that. I'm using the Levi-Civita notation, so I will go with the summation of J and K, epsilon I, J and K, A, J, D, K. Do you agree? That's the result of the vector that I'm looking for. So, but remember also here, D is a vector which is given by the cross product. So what I have to do, we have to calculate dk. So dk means that I have to calculate B cross C, the K component. So the K component of that indeed is equal to summation. I'm not allowed to use J and K anymore. I have to use another notation. I'm not allowed to use I as well. I use M and N. Then I have again epsilon. I'm looking for the K component. It will be K, M, and N. The first vector, which is BM, the second vector, which is Cn. So instead of dk, what I have to write summation on J and K, epsilon I, jk, aj, and then dk, I replace it with the summation of M and N, epsilon K, M, N, BM, Cn. Good. I don't believe that there is any problem because that's the definition that we have. So, and then now I have J, K. Also, I have M and N. That's a summation that I do have. Well, for simplicity, what I will do, because I don't care about J, M, and N for the time being, then I have AJ, BM, Cn, but I have another summation of K. Remember, all of them, they are independent of K. And then I have epsilon I, J, K, epsilon K, M, N. That is what I have, and the summation is over K, right? Okay, so any problem, any questions? I don't see the chat room. Okay.
There is so far no questions.
No questions. Okay. Okay. So now what I have to do, I have to do the calculation of these epsilon ijk, epsilon kmn. Okay. And do you remember what I say that epsilon ijk, epsilon mnk, that is equal to delta of I, summation is over k, im, delta of jn minus delta of in, delta of jm. And these are the delta chronicers. But the summation here is kmn. So I have to rearrange these. I have to rearrange these such a way that I will get exactly the same formalism that I have here. So if you remember epsilon 1, 2, 3, what was the result? +1. What is happening when I swap the two together? So what I mean, what is the result of epsilon 1, 3, 2? So it was 1, 2, 3. That was positive. Now what I will go 1, then 3, then 2. So that will be negative. So that result is -1. So whenever the two indices are swapped, then the sign will be negative. So indeed, I can write this as a general formalism. Epsilon of m, n, and k is equal to minus epsilon of m, k, n. So what I did, I swapped n and k here. So, okay. And now I will swap it another time. So now let's go with a different way. So my apologies, I want to do something else. So let's do that. Epsilon k, m, and n. That will be, I'm swapping these two together. Epsilon, that will be minus epsilon m, k, and n. Then I will do the swap of these two again. That will be minus epsilon m, n, and k. That is equal to plus epsilon m, n, k. So indeed, with this trick, I can show to you that is identical to epsilon M, N, and K, because I'm swapping it twice, the indices together. Good. So I will erase these parts because I don't need it. Maybe you will need it for the lecture notes. So I will take it down somewhere else. Okay. So summation of J, M, and N, AJ, BM, CN, summation of K, epsilon IJK, epsilon MNK is equal to delta of IM, delta of JN, minus delta of IN, delta of JM. So this means that I have summation of J, M, and N, A, J, B, M, C, N, delta of I, M, delta of J, N, and then minus summation of J, M, and N, A, J, B, M, C, N, delta of I, N, delta of J, M. So delta chronica had the property that whenever I is not equal to M, that is 0, but whenever I is equal to M, that is 1. So it means that instead of M here, all will be replaced by I. So M will be replaced by I, and the summation over M will be gone. And for the I and J and N, also this means that N will be replaced by J, and the summation on N also will be gone. So the result will be summation on J, AJ, BI, and CJ. Okay. And the last part will be the summation on AJ, BJ, and CI. So indeed, the total relation will be the summation on J, AJ, BI, CJ minus AJ, BJ, CI. That will be the result that I was looking for. So that's a relationship that we were expecting. Okay. Okay. Yeah.
One has asked, how about the magnitude of the compound product?
Would it be possible to repeat it again, please?
How about the magnitude of the compound product? What they've asked a while ago.
Oh, of the compound product. I'm not following what is exactly the question. Well, Isa, you may repeat it again. Sorry. So well, just to conclude this part, and thank you very much, Wijdan, if I'm not Wijdan, yes. And let's just conclude this. So remember, these, well, let me again take this part down. It's too complicated now. Okay, it's crowded. Okay. So here we have BI, here we have a CI, and the summation is over J. So indeed, I can write it as a BI, the summation on J, AJ, CJ, minus CI, the summation on AJ, BJ. What's that? Essentially, this is A dot C, and this one is A dot B. So indeed, what I'm looking for, which it was A, remember, it was A cross B cross C, the I component, so A cross B cross C, the IS component is given by BI A dot C minus CI A dot B. So means that A cross B cross C, the vector that you are looking is B vector A dot C minus C vector A dot B. So that's a conclusion that we do have for the time being. Okay. Now we can go with the questions. Wijdan, if you have.
There is no question.
Okay,
Oh,
perfect.
but Muhammad Isa has written he means the magnitude of bracket A times B, close bracket, times C.
Okay, this is exactly the magnitude that I say. So you have to go with the magnitude of B vector. Okay, so yeah, you have to go at this multiplication all together and see what it will be the result. Is
There's
that
no more questions.
okay? Yeah. So it will be if you are looking for A cross B cross C, the magnitude which is I say that is B A dot C minus C A dot B. So now the question is that what is going on with the magnitude? So then you have to do the summation of the two. So it will be B1 minus C1 with a, oh, I have to write it down, sorry. A dot B minus C1, A dot C, A dot B, sorry. That's what we call it X hat. And the same way you write it for Y hat, the same way that you write it for the Z hat. And then you are asking for the magnitude that will be B1 A dot C power of 2. Sorry. Minus C1 A dot B power of 2 plus the same that you will have for the rest, which is will be B2 A dot C minus C2 A dot B power of 2 plus the other one power of 1/2. That's the magnitude. Okay. Well, so far so good. So we let's go back and see. Well, we have almost 37 minutes, so I can define some other operators. So far, we were able to determine the vector space, and we say, well, what is the relationship? We had also the scalar quantity, and we say that all of them, they are changing according to the vector's quantity. They have to change according to specific rules of rotation, and we determine that one as a vector in that specific space, and then we determine some property of them, like associativity, commutations that we had between the plus of the two vectors, and then we determined the products, which one of them was a scalar product, the other one was a vector product, which we call it the cross, and we look into the property of them and the way that also you can mix them together, and you can describe the algebraic approach and also the geometrical approach for our vector space. So far, we are familiar with these sort of calculations. Now let's go a little bit more than this, and assuming that, well, I have a vector of, let's say, A, which can be a function of X, Y, and Z in the three-dimensional Euclidean space, which means that also I can write it as A, X1, X2, and X3, right? So, and remember, when I write it in this way, it means that also that has A1, which is a function of X1, X2, and X3, X hat or E1, A2, X1, X2, x3, e3, sorry, e2, a3, x1, x2, and x3, 3. Wonderful. So that's a vector that I have, and these vectors are position dependent. So for example, that can be a fluid, which is, let's say, which is moving. So assuming that you are going to one of the mountains in Kurdistan and you will see a spring, and then you look at the river and you will see that in some part, the flow of water is different in some other places. And then the velocity that you define it for each of those, let's say, individual molecules there, they are different. So they are depending on where this water is moving. So it can be in the depth. So here, for example, the velocity, it can be lower, while in the surface, the velocity can be higher. So it depends on the Z direction. It depends on the X also, and also on the Y direction. So for example, if you go to edges of these river, you will see lower velocity and etc. So this is one of the example that what we call it, we have a vector field. And in other cases, for example, you may have an object which is feeling a specific force. So the force here is again determined on this specific particle of M and has a certain quantity, which can be only function of one of the arguments. It can be function of 2 or 3 arguments there. So remember, that's a vector. And also you can have a scalar quantity of A, which can be also function of X, Y, and Z, or function of X1, X2, and X3. Okay, so remember, the vector also can be a function. Also, scalar can be a function of the coordinate. Assuming that you have a function of f, which is a scalar function, which is a function of x, and you want to look what is happening when x is changed to be x plus dx. I want to understand how this function is changed as well. So it means that the change in the function of f is given by df dx multiplied by dx. Do you agree? Because f is only function of x. And that's a small changes you have. Or if you want to understand, I mean, you know, in terms of infinitely small or incremental displacement, I would say that delta f is given by df dx delta x. If you move it a little bit, and that's the consequence, and that should be evaluated at the x equal to x. Okay. Now, what happens when my function is more complicated? So f is a function of x and y. I want to understand what is happening when x is changed to be x plus dx, and also y is changed to be y plus dy. Now I am asking you what happens with the function of f, and I'm changing x to x plus dx and y to y plus dy. And I'm looking at the difference between the two. What is happening with the df? So df now has 2 contributions, one due to the change of x and the other one due to the change of y. So for infinity small, then you will get partial derivative of f with respect to x, dx, partial derivative of f with respect to y, dy. Okay? And remember, when we use the word of partial derivative, means that you take the derivative of f only with respect to that specific argument, which is x. Okay? And in LaTeX, by the way, they use the word of partial. So if f is a function of x1, x2, and x3, then I'm asking you what is going on with the df. Then clearly df of x1, x2, and x3, then the result will be derivative of f with respect to x1, dx1 plus derivative of f with respect to x2, dx2 plus derivative of f with respect to x3, dx3. Note that f is a scalar quantity. What is happening with the dx vector or dr, let's call it in this way? Sorry. The coordinate are, if you remember, we defined it as x1, x hat, y1, or let's say x2, let's call it e1, e2, x3, e3. Assuming that e1, e2, and e3, they are orthogonal to each other, and they are constant, by the way, assuming that these are in Euclidean space. In space. So dr, indeed, since e1, e2, and e3, they are constant, means that the only changes that happens in the infinitely small direction of x1, e1, dx2, e2, dx3, e3. That is the infinitely small vector incremental vector of dr. So, and if you look at this, and if you look at that, it seems that the changes, the derivative in function of f, it's somehow introducing a new vector. And what is this new vector? Is the vector of derivative of f with respect to x1 in the direction of e1, derivative of f with respect to x2 in the direction of e2, derivative of f with respect to x3 in the direction of e3. And that's a new vector that I have it, which is, remember, that is built up from a scalar quantity, from a scalar quantity of f, okay? Which is, of course, remember that f is a function of x1, x2, and x3. And df, indeed, here, look at the df. df, it seems that is given by the dot product of the two vector of these, dot product with dx1 e1 plus dx2 e2 plus dx3 e3. And the result of the dot product, as we described previously, that will be e dot e dot, the e1 dot e1, e1 dot e2, which will be 0, e1 dot e3 will be 0. So the only component that you will have is derivative of f with respect to x1, dx1, and the rest, which is the derivative of f, x2, and dx2, and derivative of f with respect to x3, x3. So the changes in the function of f, it seems that is given by a new vector that is built up, dot the displacement in that space. And this new vector, we call it gradient of function f, okay? It can be written as a gradient like this. And remember, that's a scalar quantity. Or in a modern textbook, they write it as a gradient of f. Okay, so since this is a vector. I will add a tilde symbol on the top of this, okay? So now I introduce an operator. This is what I mean by operator. They call it del operator, or they call it nabla operator, is up to you. You can call it del, which this del operator, indeed, it should act on a scalar, okay? So what is this del operator? Is derivative with respect to x1, e1, plus e2, derivative with respect to x2, plus e3, derivative with respect to x3. Or in the Cartesian coordinate that I say, that will be x hat derivative with respect to x, plus y hat derivative with respect to y, plus z hat derivative with respect to z. Okay? Is a vector that I determine. So clearly gradient of, let's say, phi x, the result simply will be x derivative with respect to phi, which will be the full derivative now, phi of x with respect to x, which will be x hat d phi dx. So, which is a vector along x direction, x hat direction. I have to prove to you that's also a vector. How should I prove that to you? Because not anything that I drive it in terms of x hat, y hat, they are vector, but also I have to show that upon rotation, also they form a specific way. And let's do that. So assuming that I have the derivative of a scalar function, okay, let's say that I have a scalar function of phi, and this scalar function is function of x, y, and z, means that if I do a rotation of a coordinate, let's go with a phi capital just to make sure, rotation of alpha, then I will get a new function of x prime, y prime, and z prime. These look like that. So I have x, y, and I do a rotation of x prime, y prime. And now the angle is not phi, but is alpha, for example. It doesn't matter, really. It can be anything. And now I have a scalar quantity in this space, which is phi of x, y, and z. If you do a rotation still, that is a phi prime of x prime, y prime, and z prime, which is these two, they're identical. So phi of x, y, and z is equal to phi prime of x prime, y prime, and z prime. Remember, in this course, I am not using the prime for the derivative. Prime is a sign for me, is like number one. So it's look like phi 1, x1, and etc. So which I don't want to write them down, okay? So that is a scalar quantity which is not changed upon the rotation. But however, now I introduce a new vector, which was derivative of phi with respect to x, derivative of phi with respect to y, derivative of phi with respect to z. And also, of course, I can do the rotation, and I have derivative of phi prime with respect to x prime, derivative of phi prime with respect to y prime, derivative of phi prime with respect to z prime. And now I have to show, or let's do that. We have to show that this is a vector. How do we show this? So let's start with phi prime of x prime, y prime, and z prime. And what I want to show that derivative of these with respect to x prime has a certain value. Okay. Now I will change from x prime to x prime 1, y prime to x prime 2, z prime to x prime 3, and the same, x is equal to x1, y is equal to x2, and z is equal to x3. So indeed, I want to calculate what is happening with the derivative of phi prime of x prime 1, x prime 2, x prime 3 with respect to any x prime I. I want to calculate what's happening with these. Okay, it can be 1, it can be 2, it can be 3. So this is indeed the vector that I have it. So let's do the calculation. So if you agree that this is a scalar quantity, so this means that that also is equal to if x1, x2, and x3. So means that that is equal to derivative of phi of x1, x2, and x3 with respect to derivative of x prime I. So if you do a rotation here, as you see here, x1, x2, and x3, then that will be x prime 1 and x prime 2. So when you do a rotation, there is a relationship between x prime and x1, x2, and x3, x prime 2, x1, x2, and x3. So if you take the derivative, it means that I have to take care of all of the partial derivatives here. So now the function is a function of x1, x2, and x3. Then I have to do the chain rule. So indeed, I have to take the derivative of phi of x1, x2, and x3 with respect to x1, then the derivative of x1 with respect to x prime I. Then the same for x2. I have to take the derivative with respect to x2, and then derivative of x2 with respect to x prime I. And the same for the last index, which is last argument, which is x3, x1, x2, and x3 with respect to x3. And then I have the derivative of x3 with respect to x prime I. What is that, guys? Do you remember? That was AI1. What is that? AI2. What is that? AI3. So indeed, the derivative of phi prime with respect to x prime I is equal to AI1 derivative of phi, remember, is not prime here, with respect to x1 plus AI2 derivative of phi with respect to x2, AI3 derivative of phi with respect to x3, which I can write it in the compact form, that is a summation of Aij derivative of phi with respect to derivative of j. And the summation is over j. So then what I see that this is a vector which I can call it as A prime I equal to summation of j, Aij. And what about this? This another vector is in non-rotating coordinate, which is Aj. So I see that the derivative with respect to x prime I is acting like a vector. So indeed, derivative with respect to x prime I, or derivative with respect to xj, they are vectors. And they are connecting with each other with the transformation that I just described, which is a vector transformation, or I call it later on tensor 1 rank 1 transformation. Okay, So good. So, I don't think that there is any problem, and I can say that, well, gradient of a scalar, which a scalar is phi, is a vector. And what is going on with the components of the vector is derivative with respect to x1 is the first component, which is, I call it, I don't know if you want to call it A1. The second component is derivative of phi with respect to x2, which is A2. Derivative of phi with respect to x3, which is A3. Sometimes mathematicians, they don't like to write derivative of x1. Simply, they write it as derivative 1. This means that you are taking the derivative with respect to the argument of x1, and derivative with respect to x2 also we will write it as 2. Derivative with respect to 3 also we write it as 3. So indeed, some people, they write that as derivative of phi with 1, derivative of phi with respect to x2, derivative of phi with respect to x3. So remember, that's a short notation, and that's what we call it the gradient. Okay, so that's the definition of a gradient. Any questions, if there is any? Who is
There is no question so far.
okay, lovely, Wijdan, thank you very much. So, well, of course we define things, and of course this is a vector, but what is this vector? I mean, look at the definition of that. Assuming that I have gradient of phi dot dr, which is what I say that it gives me the infinitely small value of d phi, okay? So assuming that dr, which is the incremental displacement that happens, we assume that that happens in a three-dimensional geometry. So assuming that's our coordinate, okay, which is x1, x2, and x3, or x, y, and z. Then I have a surface. This surface is formed by the function of phi, which is phi of x1, x2, and x3. There's an equation there. And then I assume that there are two small points here, or the points of P, and then I have another points Q, very, very small, but on the same curvature, on the same plane of phi constant. Phi is constant here. There's a surface of phi constant. And then I will go here, which is the point of Q. So the displacement between the two is dr here. Okay, let me enlarge it just to make it clear for you. This is what we have. This point of Q can be anywhere in the plane. It can be here, it can be here, it can be here. Any small points close, any points close to the point P. Okay, good, lovely. So now I'm asking, what is happening with the phi for point P and minus phi for the point Q? Okay, well, let's write it in a proper way. Let me just make it smaller. Okay, so what is happening with the phi of RP and phi of RQ? What is the value of them? Both of them, they are on the same surface, right? I'm looking at the, okay. So both of them, they are on the same plane, which the plane is the phi constant. So both of them, they are identical and they are a constant. Okay. And remember, RQ is RP plus dr, this small displacement that you have either on this. So what is happening with the gradient of phi dot dr? Since the changes in the potential is nothing happens, so that's equal to 0. Okay? So if the 2 points are in the same phi surface, then gradient of phi dot dr is equal to 0. What is dr? dr is the distance between the two, is the vector that is defining, and it can be any direction that you want, but in the same plane. So gradient of phi, which is a vector, dot dr for any point of Q that exists on the same surface is equal to 0. So what does it mean? That the gradient of phi is orthogonal to the dr. So means that the gradient of phi is normal to the surface. Okay? So if you have a surface of phi, a function which is from a surface, then gradient of phi is always orthogonal to that surface. Remember, that's really an important property. So if you want to find a normal to a co-phase or surfaces, then essentially you have to take the gradient. Okay. So in optics, for example, we have the co-phase surfaces, and if you want to find the k vector which is orthogonal to that, you have to take the gradient of the phase.
Sir, there are 2 questions. Shall I read them for you?
Yes, please, Vijdan, go ahead.
The first one says that, is that possible when d phi bracket x1, x2, x3 slash d prime I, only one of the x couldn't be derived to d prime I? For example, d phi bracket x2, close bracket, can be derivative to d prime I. Is that possible to happen?
Oh, I have to write it down, to be honest with you. So let me see. So your question is that, assuming that I have a d of phi of x1, x2, and x3, and d, I assume is a partial derivative, or is, yes, I assume that is a partial derivative of x prime I. Then Shania is asking, only one of the x couldn't be derived to d prime I. Well, in the case that I have it here, which was the coordinate, in general, yeah, and in general, all of them, they are linked to each other. So x1 is a function of x prime 1, x prime 2, and x prime 3, and etc. That's the reason that I expanded. But in general, yes, it can be only one of them as a function. But remember, in the rotation case that I had, no, they can, depending on the kind of rotation that you apply. In general, no, they are all depending on each other.
Yeah, the other question is gradient vector operator? If that is operator, then will the cross product with itself give 0 or non-zero? I ask because L cross L is non-zero, as L is an operator. Exactly,
is non-zero. Is a non-zero. It depends on the function. Yes, you got the point very well.
And one has asked if df equals delta f approximately.
Yes, indeed, df, well, I can write delta f. What does it mean, delta f? Depends if you write it for one function. Let's write it for one function, one argument. So f is a function of x, right? And I'm looking for delta f. What does it mean? That is f of x plus delta x minus f of x. Okay, and then this is given by derivative of f with respect to x delta x. Now, if you go to incremental way, or the infinity small dx, then the changes is not delta x, but it will be dx, and associate to this one also, the change for f will be df. It will be small. Yes. What you say is correct.
There is no more question.
Okay, lovely. So I'm trying to erase them. There is a little bit of lagging behind. So I have 5 minutes to conclude the gradient. So, well, I don't know if I have something else to tell about the gradient. So, well, gradient of phi is a vector. Okay, and we show how the vector is changing. So derivative with respect to x prime I is the summation of aij derivative with respect to xj. Okay, and now I can put phi here. The second thing is that gradient of phi is orthogonal to the surface, the surface of phi. Okay, which is a lovely one. Okay, and it also gives the shortest value. So essentially, gradient of phi dr is given by d phi, right? So indeed, what is happening when this dr is belonging to different different phis. So here the phi is equal to C1, and this one is a phi equal to C2. Okay, and dr is now, that's a point of P, and that's a point of Q because I'm changing it now. And that's a dr, and that's an infinitely small displacement that I have here. So that will be C2 minus C1, or equal to delta C. And then what I will see that gradient of phi dot dr that has the maximum value when dr is normal to the surface. So this will give you the shortest way. So remember that that is extremely useful. Why we care? We do care about gradient because in physics, many of the vectors appear as the gradient of a scalar. For example, force that we have is given by minus gradient of a phi, or you may not be familiar with that, but appears as a gradient of a potential. Or for example, in electrostatic, electric field is given by minus gradient of the scalar potential. Okay, recall scalar potential. This is electrostatic. I didn't say that is electromagnetism. Okay, it's electrostatic. So that is very, very helpful to understand. So I think after that I have to go with the divergence and the curve, but we don't have a time. I will stop here. Okay, we have 2 minutes. So I will stop here. I will stop the recording, and then we will have the discussion. Okay, thank you very much, and I will see you tomorrow. I'm available for questions if there is any.
Yeah, there's a few questions. One has asked to the definition of A cross B cross C you gave before tensors approach to define the cross product. You said alpha is simply a dot product of A dot C, and beta is minus B dot A. How did you find alpha and beta coefficients? Can you briefly comment on how you conclude this, not as evidence from the geometry you drew?
Yeah, absolutely. That's a very, very good question. And that's a homework that you will get it. So indeed, you have to do a little bit of mathematics. Is not very trivial, but I would say that it comes from linearity of the equations. So A cross B cross C is linear in A, linear in B, linear in C. So if you use this formalism, you will get the result. It's a homework, and for sure the result of the homework I will post it also with the help of the moderators here.
There's another question that goes, the gradient vector is normal to the surface. Therefore, can we make a guess that whose cross product is equal to the gradient? I mean, which vectors have made gradient vector using cross product? Is it possible?
Well, remember that the gradient is applying to a scalar, okay? Unless if you open the microphone and telling me the question, maybe I would understand it better, because the gradient is applying to a scalar, and then it will give you normal to that scalar phase, right? So I don't understand exactly what you mean by having the cross product that is equal to the gradient. I'm not following that, the cross product. So you may mean that I may define new vectors in that surface, that the cross product of the two will give you the normal vector. That's one way that you can watch it, yes.
One has asked, usually when we assign equations to the surface, but what is the meaning of surface phi equals constant?
So means that, well, whatever, for example, you have a code, let's say, I don't know, do you see my screen? So x squared plus y squared plus z squared is equal to 1, okay? This is a function, I call it f, x, y, and z, which is x squared plus y squared plus z squared. That can be any function. I mean, you know very well. So if it's equal to 1 in the three-dimensional space, that's a surface, right? Which is sphere of unit vector, right? And this is f, x, y, z equal to 1, which is a constant here. What is about 2? That will be another surface here, which the radius is equal to square root of 2, and etc. So that's what I mean by this. I hope that is clear.
Sir, we have 2 attendants want to participate through mic. If possible, we have Mr. Isa and Dr. Bhutan.
Of course. You have to let them speak. So you have to allow them to promote to panelists. No, you have to allow them to speak. Yes. Mohammed Isa.
Hello.
Hi.
Hi, Dr. Ibrahimi. Thank you, Dr. Ibrahimi. Thanks, and I appreciate your time and your colleagues' time. I appreciate your effort. I have a question. You mentioned in photonics, like that co-phase is kind of like a surface that you use the gradient. So I'm wondering how you identify or how you write the mathematical equation of the phi function, like the scalar phi.
Yes, it's a good question.
So like in like experimentally in laboratory.
Yes, yes, I will write it down. Okay.
Thanks.
Yeah, of course. So let's go to so you see the screen. So I will write it one in a couple of examples. So wave is propagating in one specific direction, right?
Yeah.
And let's call it that this wave is propagating in the plane of X, Y, and Z. under the angle of, let's say, 30 degrees. Pi divided by 6. So what is the field? I mean, what is the wave that is propagating? Is a planar wave? Is a spherical wave? Is what? That's a question, okay, that you do have. So
It depends.
yeah, exactly. Depends on the situation that we do have. For example, that was an example that I gave it, and I call it this. This is the spherical wave. Is what you have it here, which is given by R, right? The phase that you have for the argument that is equal to, for example, KR. Phi here, X, Y, and Z is equal to KR. And R means that square root of X squared plus Y squared plus Z squared. That's a way that, for example, if you have a lamp here, and that's a way that the wave is propagating, and that's a co-phase surfaces, essentially.
Okay.
Okay. Now I'm asking you what is going on with this wave, which is propagating in a spherical fashion. What is happening with the K vector? The K vector is orthogonal to that one, right?
That's right.
And how do you calculate the K vector? You take the gradient of phase.
Yeah.
And when you take the
Of
gradient,
the two sides, like actually.
exactly, you will get the gradient of R, right?
Sure. Yeah.
And what is the gradient of R? You can do the calculation, and that will be given by KR.
Yeah, exactly.
That's exactly the K vector that you are expecting. So you have K, essentially, we can write it as a KR, R hat, which is the spherical wave which is propagating. You can assume something else. You can assume, for example, is one of those fluorescent lamp in my office, which I have it, which is a cylindrical one. So choosing the coordinate, which is a cylindrical one, then means that it's in X and Y. Oh, let's go Z, X and Y. Now the wave that is propagating is look like a cylinder right here from these tungsten lamp. Sorry, these fluorescent lamp. Okay.
Okay.
This is the co-phase. And if you write the equation for this, the co-phase equation will be X squared plus Y squared equal to a constant. That's the co-phase, power of 1/2. That's a phase that you have. And now I'm asking you what is going on with the K vector. If you do the K vector is a gradient of phi, and essentially that will give you K rho hat, because there is no Z component along these. It will not be propagating, only along this direction will be propagating.
So what I've understood from your explanation, most of the like the objects in the laboratory or under experiment, it should be like regular geometrical objects, right? Right, spheres, like cylinders, those kind of things, right?
Well, don't get me wrong, okay?
No. I'm sorry. I'm saying that if
Yeah.
like it's like a curved space, like if like curved surface. So what happened when we don't have like the right equation for this? So we have to like do the experiment like locally or something.
Well, get the phase expression. Okay. Get
Sure.
the expression of the phase from the equations. For example, it can be Lagrangian, many different of them. And then what you have to do, you have to take the gradient of phi, and you will get the K vectors. That's it.
I know. What if we don't have phi? Like we have objects like physically, so we have to make the equation. We have to find the equation, the right equation for that surface. So
you can find it. You can find it out at all. I mean, give me anything that you want. I can write it down. Might not be exact solution, but I can find the analytical expression, or you can use the numerical softwares, which you can place the objects there, and then it will tell you what is happening. For example,
so
many nano antennas there, right? And these many nano antennas, they will work like a point sources. Of course, there are many of them. You may have no analytical expression for all of them, but you may get a numerical solution for these, and you will get the phases, and you can fit an equation on the phases, and then you can take a gradient and you will get the k vectors.
Okay, thanks. That was I was looking for. So it should be like an approximate, right?
Physics without approximation is nothing.
Yeah. Thank you very much. I appreciate it.
Of course.
Thanks.
Sure. There were other questions as well, or not?
No, that's it. Thank you.
There's no more questions.
Okay, I would like to thank the moderators. Thank you very much. People here, Jamil, Nazanin, Vijdan, thank you very much. Dr. Astrin as well, and Dam, Judy, and Lena, and Sonia. Thank you very much, and Dr. Virya, for all of you, for your time, taking care of the questions, and also helping me with this course. Thanks a lot.
Thank you. Thank you too.
Yeah. I will see you tomorrow, of course. Thank you.
I will see you. Bye-bye.
Thank you, sir. Have a great time.